Rotation of axes. In this slideshow we'll have several demonstrations detailing the arithmetic associated with rotation of axes. In our first example, we will express the equation xy equal 1 in terms of new x prime y prime coordinates by rotating the axes through a 45-degree angle. And then we will describe the new equation in terms of conic information. So what we're going to do here is we're going to let theta be equal 45 degrees, and we're going to use the equations in the new coordinate system, the rotation equations, and they're written out here with 45 degrees substituted in for theta, and then we evaluate the sine and cosine of 45 degrees, which is root 2 over 2. So in the old coordinate system xy, they are related to the new coordinate system x prime y prime by these equations listed in 1. Now we're going to solve for x prime and y prime, and we have these equations that are listed in 2. So we have square root 2 over 2x plus square root 2 over 2y for x prime, and for y prime we have negative square root 2 over 2x plus square root 2 over 2y. This is for plotting purposes in the new rotated axis system. So for example, in the xy plane, the vertices are located at 1, 1 and negative 1, negative 1. In the xy plane, or the x prime y prime plane, the rotated axes, the location of the vertices will be at negative root 2, 0 and root 2, 0. So the rotation has essentially redescribed the location in space. It's the same location in space, but they're being described in a new coordinate system. Now substituting these rotation equations into our original xy equal 1, we have x, which is root 2 over 2 x prime minus y prime, and y, which is root 2 over 2 times x prime plus y prime. We go ahead and multiply this out, and we end up with 1/2 times quantity x prime squared minus y prime squared, and we have 1/2 times that quantity equal to 1. And therefore we go ahead and distribute the 1/2, and we have a new looking equation using the rotated coordinate system. And matching up our formats, this is the standard form for a hyperbola. So using the rotated axis, we have the following information, with a equal to the square root of 2, b equal to the square root of 2, and c equal to 2 in general. So the ordered pairs are in the rotated axes x prime y prime system. So on this chart here we have a lot of information that we use when we're discussing the hyperbola. The orientation will be that the transverse axis is on the x prime axis. Remember, all of this is in relation to the new coordinate system. The center is still at the origin. The foci is at plus or minus 2, 0. The vertices are at plus or minus square root 2, 0. The eccentricity can be found by taking the value of c and divided by a. Basically the distance from the center to the focus divided by the distance from the center to the vertex. And when we do that ratio, we get the square root of 2, which is approximately 1.414. The length of the lattice rectum, 2b squared over a. Plug in those values and we end up with the square root of 8. The directrices is given in the new rotated coordinate system, x prime equal to plus or minus 1. And the asymptotes, again, are given in the new rotated coordinate system, y prime is equal to plus or minus x prime. And here's a graph of the conic section with the rotated coordinate system. So here we can see that the x prime line and the y prime line, these are in red. These are the new coordinate system. The dashed green lines represent the asymptotes in the new coordinate system. And here we also have the center, the foci, and the vertices labeled as well. So this is still a hyperbola, but the original coordinate system has been rotated 45 degrees so that the red lines correspond to the new coordinate system, and therefore we describe this hyperbola relative to that rotated axis. Our second example asks us to analyze the equation x squared plus square root of 3 times xy plus 2y squared minus 10 equals 0. Now, since there's an xy term present, we have to rotate the axes. We do this in order to simplify the discussion and also describe a much simpler conic section in terms of a new coordinate system as soon as we figure out the angle of rotation. So that's what we're going to do first. So we're going to let a be 1, b be the square root of 3, and c equal 2 from our general conic equation. And the angle to rotate is the acute angle satisfying the cotangent of 2 theta is equal to a minus c over b. Plug in those values for a, b, and c, and you end up with negative 1 over the square root of 3. So we have to do the inverse cotangent of negative 1 over root 3 and then divide that result by 2. And when we do that, we are going to get 60 degrees. Now remember, the angle of rotation is an acute angle. So when you do this directly, you'll have negative 30 degrees. But then you go ahead and take the complement of that to get that acute angle, and it ends up being positive 60. Now that detail is omitted because we specifically state that we're rotating through an acute angle in the very second sentence up here. So using the rotation of axes formulas, again, we plug in the 60 degrees for theta, the angle of rotation. Go ahead and evaluate the sine and cosine of those, and we have x in terms of x prime, y prime, and we have y in terms of x prime, y prime. So here are the rotation formulas. And again, these will be used for plotting purposes. When we substitute those values into our original equation, so x is going to get this x prime minus root 3 y prime times 1/2, okay? And we're going to say y is that 1/2 root 3 x prime plus y prime. When we plug those equations in for x and y and start expanding out and combining like terms and simplifying, all of the details are here on the slide. Our final result ends up being x prime squared over 4 plus y prime squared over 20 is equal to 1. So the details are here. I encourage that you fill in the reasons why or the steps as far as what you're doing, like I'm expanding a binomial, combining terms, distributing, things of that nature. So we do end up with our equation down here in the lower right. X prime squared over 4 plus y prime squared over 20 is equal to 1. And that is the equation of an ellipse. So using the rotated axes, we have the following information. Now a is going to be the square root of 20 and b is going to be 2. Please remember that in the equation of the ellipse, a is always assumed to be the larger value. Now square root of 20 is about 2 root 5, so it's a little bit bigger than 2. C, of course, is going to be the square root of 20 minus 4, which ends up being 4. So again, the ordered pairs listed in the table below correspond to the rotated axes, the x prime, y prime plane. The orientation, the major axis is on the y prime axis. The center is at the origin. The foci is at 0 plus or minus 4. That's the value of C. The vertices are at 0 plus or minus 2 root 5. That's the value of A, from the center. The eccentricity, the value of C divided by the value of A, 4 over square root 20, is approximately 0.89. This is less than 1. Ellipses have eccentricities between 0 and 1. The length of the major and minor axes are given here as 4 root 5 and 4 respectively. The length of the latest rectum is going to be 4 divided by root 5. The calculation is here. And the directrices to the ellipses are located at y prime equal to plus or minus 5. So these are horizontal lines in the y prime coordinate system. And here's a graph of the conic section. Now remember that it was oriented vertically, but the angle of rotation starts from the horizontal axis. So starting from the horizontal, and rotating up to the red line, that's the angle of rotation that's performed. But here we can see the graph of the ellipse. We have the foci, the center, the vertices, and negative 2, 0, and 2, 0 correspond to the co-vertices in the x prime, y prime plane. So here's the graph of this particular conic section rotated through the angle of rotation. Our third example asks us to analyze the equation 4x squared minus 4xy plus y squared plus 5 root 5x plus 5 equals 0. Again, there's an xy term present, so we have to rotate the axes. Using our general form of a conic, we identify capital A as 4, capital B as negative 4, and capital C as 1. The angle to rotate is the acute angle satisfying the cotangent of 2 theta equal to A minus C over B. Plug in on our numbers, we get negative 3/4. So the angle of rotation is going to be 1/2 the inverse cotangent of negative 3/4. This is not an angle we may be familiar with using the unit circle. So our recourse is to rewrite using sines and cosines to see if we can determine a closed form for this angle. Now the reason why we want to do a closed form is because this angle is going to be, we're going to take the cosine and the sine of this angle. So I don't want to do approximations unless I absolutely have to. So what we're going to do is we're going to use some trigonometry here and some right triangles. Now we also want an acute angle, but because 2 theta, the cotangent of 2 theta ended up being a negative number, we have to consider that 2 theta is between 90 degrees and 180 degrees. It's in the second quadrant. 2 theta is. Theta will still be in the first quadrant between 45 degrees and 90 degrees. So what we're going to do is we're going to use right triangles. We know that the cotangent of an angle is adjacent over opposite. We also know that 3 squared plus 4 squared is going to be our hypotenuse squared. So we get the hypotenuse to be 5 for this particular triangle. So we can rewrite the cotangent of 2 theta as negative 3/4. We can say that's equal to negative 3 over 5 divided by 4 over 5. I divide both top and bottom by 5. I don't change the value. But this gives me an indication of the cosine of 2 theta and the sine of 2 theta. So what's going on here is we're going back to right triangles. We have evaluations of the cosine of 2 theta and the sine of 2 theta based on the work that we've done here. Remember, cotangent is cosine over sine. So we know the cosine of 2 theta has to be negative 3/5. We know the sine of 2 theta has to be 4/5. Now the negative has to go with the cosine because we already mentioned earlier that 2 theta has to be in the second quadrant between 90 degrees and 180 degrees, and we know that the cosine is negative in that spot. That's why the negative is associated with the cosine here. Now remember, we're trying to get just cosine theta and sine theta, which means I'm going to use the half angle formulas that are done here. So when I plug in the cosine of 2 theta for both these half angle formulas, do a little simplifying here, I end up with a cosine of theta being root 5 over 5 and sine of theta being 2 root 5 over 5. And these are the numbers that I'm going to use when I come to my substitution and reducing things down in the new coordinate system. So now that we have the values of sine and cosine, we can use the rotation formulas with those values involved. So determining the specific angle of rotation is not necessary here, since we need the values of sine and cosine to complete the rotation formulas. But to satisfy curiosity, the initial angle of rotation would be negative 26.56 degrees approximately. We're going to seek that acute angle between 45 and 90 degrees. We find the complement, 90 plus negative 26.56 is approximately 63.44 degrees. So that's the angle of rotation. But the work that we did previously helps us mathematically without having to approximate these angles. So the original x, after I plug in what the cosine of theta and the sine of theta are from the previous work, ends up being root 5 over 5 times the quantity x prime minus 2y prime. That's the original x. The original y in relation to the new coordinate system is going to be root 5 over 5 times the quantity 2x prime plus y prime. So those are the equations that I'm going to substitute into my original equation. So there's the original equation, 4x squared minus 4xy plus y squared plus 5 times root 5 times x plus 5 equals 0. Plugging in those x formulas and y formulas in terms of x prime and y prime, simplifying the results down gives us the quantity y prime minus 1 squared is equal to x prime. This is the equation of a parabola. Note that a equals 1 in this case, but the parabola opens left with respect to y prime. The ordered pairs listed in the table below correspond to the rotated axes, the x prime, y prime plane. So the axis of symmetry is y prime equal 1. The focus is at negative 1/4, 1. The vertex is at 0, 1. The eccentricity is 1. Eccentricity of a parabola is always identically 1 by definition. The length of the latest rectum will be 1 because a is 1 in this case. And the directrix will be located at x prime equal to 5/4. It'll be that line. And here's a graph of this rotated conic. So here is the directrix, and you may initially think, hey, that looks more like a slanted line, but remember, you have to look at it in terms of x prime and y prime, the red coordinate axes here. And this dashed directrix is parallel to the y prime axis, meaning that x prime is fixed at a number. The focus and vertex are listed here as well, and this is your diagram. The axis of symmetry is that line connecting both the focus and the vertex. Notice that with respect to y prime, it is a horizontal line because it's parallel to the x prime axis. So while this diagram looks a little bit unorthodox, it does correspond to the information we've listed with respect to the x prime, y prime coordinate system, the red axes drawn here. Thank you for your time and attention.